Hi, everyone. Welcome to the talk, and today I'll present our work, Don't Waste My Effort, Pruning Redundant Sanitizer Checks by Developer-Implemented Type Checks. My name is Yizhuo Zhai from Georgia Tech. Currently, I'm a postdoc with Professor Kim. This is my last work during my PhD in the UC Riverside with all those awesome professors. And this is a joint work from UC Riverside and US Army Research Lab. So this work targets at type confusion, which happens when an object of type A is misused as another incompatible type B. During this presentation, I will use the C++ as an example to show our problems and ideas behind. So given one base class declared as shape, it defines a field called type, and then two subclasses derived from the shape. One is circle, another is square, with additional field unique to them. If we look at the memory layout of these three classes, the shape will have one field, and the circle and square have two fields individually. There are usually two types of the casting along with the program. One is upcast. It casts the derived class back to the parent class. This cast is always safe, because if we are visiting the field to the derived class from the basic class, then since they share the same field, there will be no problem, and all the visiting will be valid. However, another of type casting, downcast, it casts the parent class back to the derived class. It's not always safe, because if we cast a pointer of the base class down to the pointer to the derived class, here's the example from shape to circle, then visit the radius field by using the downcasted pointer, then we will visit an invalid memory because the radius field is out of the access scope of the shape. This is unsafe and could cause the system crash or arbitrary code execution. There are usually three types of dynamic mitigations for this. The first is C++ offers dynamic cast operations. In these operations, they will perform the runtime information checks. So the basic idea is that they will extract the type information of the derived class through the virtual function table, and then do the compatible check. There are two limitations of those approach. First, the base class of the derived class should has the virtual table. It means that we at least need to define one virtual function in the base class. Second, because the type information from derived class to the parent class are chained together, when we traverse this linked list to get the type information, it introduces many overhead to the program. So this approach cannot provide the full protection to a program, and also it introduces the high overhead and prohibits for performance critical software such as Chrome. The second approach is a sanitizer approach. This approach encoded all the compatible types into a metadata for the object at the allocation site. And those objects will be organized in some high-efficiency lookup data structures, such as binary tree. In sanitizer approach, during the compilation time, they will insert a sanitizer check before each cast. So along with the program execution, before the cast happens, the sanitizer check will look for the concrete object and then extract the compatible types to perform the type check. By using this approach, we can get a full protection from type confusion for the program. However, it also introduces the high overhead because of this frequently called sanitizer check. The last approach is the customer runtime type check, time information, in short, RTTI. If we still remember the first field declared in the basic class called type, developers usually initialize this type along with an object location, and then before it do the casting, it check if this type is a specific type they want. By using this approach, it can introduce low overhead because there's only two operations, a memory read and a comparison. However, it cannot provide the full protection because it all depends on developers' behavior. First, they may not insert such type information into the class definition. Second, before the cast, they may or may not insert such type information check. So the question is, can we combine the last two approaches together for the cast that can be protected by developers' inserted checks? We don't use the sanitizer's check. And for those checks that we do not have the developers' inserted check, we fall back to the sanitizer's approach. If so, we can also combine the advantage together to get a full protection and a low overhead. And the answer is yes. So that's our approach, Pruning-file approach. Given the program source code as the input, we will perform first the custom type information inference. In this step, we collect all the classes and organize them via the type hierarchy. Then we identify type information and store them in the database. And after we got those type information, we can perform the static safe casting verification. In this step, we compile the source code into the LLVM-IR. Then by using the type information in the last step, we identify the type checks. And along with the control flow analysis, we got the safe cast that protected by the developer implemented checks. Combined with the sanitizer approach, we can have the lightweight instrument program. So let's dig into some details about those two steps. First, custom RTTI inference. So the challenge here is it's highly customized by the developers. There's no standard, no document, no formal pattern for the customer RTTI. So our approach here is to systematically investigate the large C++ program and split those patterns into three categories. First category is RTTI encoded in a base class field. Those four classes are all from the Chrome. This is pretty similar as what we saw in the example. In the base class, we have a class type declared, and it provides a constructor to pass in the concrete value. And three derived classes will pass in different values to indicate different classes. And in the base class, it also provides utility function for the type check. A second category, RTTI as constant. So in the base class, instead of explicitly declare a field, it declare a virtual function called shapeType and different derived class override this function and return different values to distinguish between the class. The last category is the RTTI defined as a type check function. So in the base class, it declares a couple of virtual functions and returns false. Different derived class override those virtual functions and return true to indicate different types. Given those three categories, we can perform the customer RTTI inference along with the type hierarchy. For first two categories, we first collect all the enumeration constant and check the sync if they are assigned to the field in the constructor or returned by a virtual method. And also, if they are passed in by a constructor, they cannot be changed once initialized. For the third category, as a type check function, we will check the derived class and see if they will override the return value of the virtual function defined in the base class. And also the overwritten return value is unique across the hierarchy. After getting those type informations, we'll perform the static safe casting verification. What we did is that in the IR level, we will check each comparison operations, including the if statement and switch case. If we find such a type check, then we can infer the correct type with the type information and say that if any cast is dominated by those typecasts, and also in between there is no change. If so, we can identify a safe cast protected by the developer implemented check. Here comes our implementation. So for the first part, customer RTTI identification, we use the lib clone to parse the type information. For the rest of the components, we use the LLVM version 14.0.14.5, and it contains over 9,000 lines of code in total. We also upgrade the hex type into the same version of the LLVM for comparison. And for evaluation, I'll mainly show 3 questions here. First, the prevalence of the customer RTTI. The second, how many safe casts we can identify using our approach. Third question, how much overhead we can reduce comparing with the Sanitizer's approach. To answer the first question, we select 7 popular large-scale C++ software and randomly sample some classes from them. The result shows that 6 of them contains the customer RTTI, indicating the prevalence of the customer RTTI. The second question, how many safe casts that our approach can effectively find? We put the overall table here, but I want to highlight the last big column. The first line, the total number of downcast operations under the Chrome LVM, and 1 benchmark from spec CPU 2006. And in the last line, you can see the downcast operations with type checks, meaning the safe cast we can identify. Although from the last line, those numbers look relatively small comparing with the total number of downcast operations. If we run these benchmarks and calculate the Sanitizer checks in total, the things will be different. So let's take the first line as an example. We run the speedometer benchmark, which tests the web application responses under the benchmark using the Chromium. And the hex type performs thousands of millions of Sanitizers check. But with our Pruning approach, we only perform 241 million check. It shows that our approach can effectively reduce the number of Sanitizer checks by 84%. And for the overhead reduction, we also compare our tool with the hex type. And besides the raw number, I also put the relative percent at the end of each line. Here comes our conclusion. Customer RTTI is widely used in preventing the type confusion. And we propose Pruning, which is an automatic tool to combine the Sanitizer's approach and customer RTTI to ensure full protection with minimum overhead to mitigate type confusion. From the evaluation, by comparing our approach to the Sanitizer's approach, we can reduce the overhead by 25% to 75% for large-scale C++ software. And we are working on open sourcing it to the GitHub. Thanks for listening. I'll be in the job market this year, so feel free to talk to me offline. And now I'm happy to take questions.